Welcome. Today we will see thick cylindrical shells subjected to an internal pressure. When the ratio of the inner diameter of the cylinder to the wall thickness is greater than 10 to 15, the cylinder is called as thick cylinder. Hydraulic cylinders, high pressure pipes and gun barrels are examples of thick cylinders. The radial stress sigma r is neglected in thin cylinders, but it is of significant magnitude in case of thick cylinders. There are number of equations for the design of thick cylinders. The choice of equation depends upon two parameters: cylinder material, that is whether brittle or ductile, and condition of cylinder ends, that is open or closed. In the design of thick cylindrical shells, the following equations are mostly used: first, Lami's equation; second, Firmi's equation; third, Clapeyron's equation. Now we will see Lami's equation. When the material of the cylinder is brittle, such as cast iron or cast steel, Lami's equation is used to determine the wall thickness. It is based on the maximum principal stress theory of failure, whereas maximum principal stress is equated to permissible stress for the material. Three principal stresses at the inner surface of the cylinder are as follows: sigma r is equal to minus pi, equation 1; sigma t is equal to pi plus pi into bracket do square plus di square divided by do square minus di square, equation 2; and sigma l is equal to pi di square divided by do square minus di square, equation 3. Therefore, sigma t is greater than sigma m greater than sigma r. Hence, sigma t is the criterion of design. From the equation 2, sigma t upon pi is equal to do square by di square divided by do square minus di square. Therefore, cross multiplying, sigma t into bracket do square minus di square plus pi into bracket do square plus di square. Therefore, sigma t into do square minus sigma t into di square is equal to pi into do square plus pi into di square. Therefore, rearranging the terms, sigma t into do square minus pi into do square is equal to sigma t into di square plus pi into di square, taking do square and di square outside. Therefore, do square upon di square is equal to sigma t plus pi divided by sigma t minus pi. Therefore, do divided by di bracket square is equal to sigma t plus pi divided by sigma t minus pi. Therefore, do divided by di is equal to square root of sigma t plus pi divided by sigma t minus pi. Substituting do is equal to di plus 2t in the equation. Therefore, di plus 2t divided by di is equal to square root of sigma t plus pi divided by sigma t minus pi. Therefore, 1 plus 2t divided by di is equal to square root of sigma t plus pi divided by sigma t minus pi. Therefore, 2t divided by di is equal to square root of sigma t plus pi divided by sigma t minus pi minus 1. Therefore, t is equal to ti divided by 2 into square root of sigma t plus pi divided by sigma t minus pi minus 1, where sigma t is equal to s ut divided by fs. Now we will see Birney's equation. In case of open-end cylinders such as pump cylinders, ramps, gun barrels, etc., made of ductile metal, that is low carbon steel, brass, bronze, and aluminum alloys, the allowable stresses cannot be determined by means of maximum stress theory of failure. In such cases, the maximum strain theory is used. According to this theory, the failure occurs when the strain reaches a limiting value. Birney's equation for the wall thickness of a cylinder is given by T is equal to di divided by 2 into bracket square root of sigma plus 1 minus mu into pi divided by sigma minus into bracket 1 plus mu into pi minus 1 bracket 1. Now we will see Clapeyron's equation. This equation is based on the maximum strain theory of failure, but it is applied to closed-end cylinders or cylinders fitted with heads made of ductile material. According to this equation, the thickness of a cylinder is given by T is equal to di divided by 2 into bracket square root of sigma plus 1 minus 2 mu into pi divided by sigma minus 1 plus mu into pi minus 1, where sigma is equal to syt divided by fs. Now we will see autofretting or pre-stressing. Autofretting is a process of pre-stressing a cylinder before using it in service. It is used in case of high pressure cylinders and gun barrels. When the cylinder is subjected to an internal pressure, the circumferential stress sigma t at the inner surface limits the pressure capacity of the cylinder. In the pre-stressing process, residual compressive stresses are developed at the inner surface. When the cylinder is loaded in service, the residual compressive stresses at the inner surface begin to decrease, become zero, and finally become tensile as the pressure is gradually increased. Auto-fittage increases the pressure capacity of the cylinder. It has another advantage that the residual compressive stresses close the cracks within the cylinder, resulting in increased end. There are three methods of pre-stressing the cylinder. They are as follows. First, compound cylinder. It consists of two concentric cylinders with outer cylinder shrunk onto the inner one. This induces compressive stresses in the inner cylinder. Compound cylinder is extensively used in service. A compound cylinder consisting of a cylinder and a jacket is shown in figure A. The inner diameter of the jacket is slightly smaller than the outer diameter of the cylinder. This is the compound cylinder A, this is the cylinder A, this is the jacket. When the jacket is heated, it expands sufficiently to move over the cylinder. As the jacket cools, it tends to contract onto the inner cylinder, which induces residual compressive stresses. There is a shrinkage pressure P between the cylinder and the jacket. The pressure P tends to contract the cylinder and expand the jacket as shown in figures B and C. The shrinkage pressure P can be evaluated from the below equation for a given amount of interference delta. If delta is equal to P d2 divided by capital E, that is Young's modulus, into bracket 2d2 square into bracket d3 square minus d1 square divided by d3 square minus d2 square into d2 square minus d1 square. The resultant stresses in a compound cylinder are found by superimposing the two stresses due to shrink fit and those due to internal pressure. Second method, overloading cylinder. The second method consists of overloading the cylinder before it is put into service. The overloading pressure is adjusted in such a way that a portion of the cylinder near the inner diameter is subjected to stresses in the plastic range, while the outer portion is still in the elastic range. When the pressure is released, the outer portion contracts, exerting pressure on the inner portion, which has undergone permanent deformation. This induces residual compressive stresses at the inner surface. Third is the wire method. In the third method, a wire under tension is closely wound around the cylinder, which results in residual compressive stresses. Okay, thank you very much.